Carbon, element 6, operates with 6 protons in its nucleus and 4 electrons in its outer valence shell. To achieve atomic stability, it requires a full set of 8. However, its 6 protons lack the electromagnetic force required to pull 4 extra electrons away from other atoms. This makes standard ionic bonding, stealing or giving away electrons, impossible. It cannot pull in 4 external electrons to form a negative ion, and ejecting its own 4 to form a positive ion requires a massive amount of energy. To bypass this atomic gridlock, carbon shares its electrons. By overlapping its orbits with other atoms, like hydrogen, it allows electrons to pass back and forth, creating a stable connection known as a covalent bond. Because it has 4 empty slots in that outer shell, a single carbon atom can form 4 of these covalent bonds simultaneously. This capability is called tetravalency. Those 4 connection points allow carbon to bond with other carbon atoms, creating a daisy chain effect called catenation. This property enables carbon to link endlessly with itself to form massive molecular structures. Because carbon lacks the force to steal electrons, it is forced to become a connector. That limitation makes it the foundational building block for every complex molecular chain in the universe. When carbon forms these covalent bonds, it reshapes its electron orbits to accommodate the incoming atoms. This process, called hybridization, dictates the final 3-dimensional shape of the molecule. Methane is the result of sp3 hybridization. When carbon forms 4 single bonds, the orbits push away from each other equally, creating a 3-dimensional tetrahedral shape with angles of exactly 109 degrees and 28 minutes. Introducing a double bond between 2 carbon atoms triggers sp2 hybridization. To accommodate that bond, the ethene molecule flattens into a 2-dimensional planar shape, widening the connection angles to 120 degrees. A triple bond requires sp hybridization. This ethine molecule snaps into a rigid straight line, forcing the bond angles to a flat 180 degrees. In carbon chemistry, the specific bond type defines the structural geometry of the entire molecule. This geometric variation drives allotropy, a phenomenon where identical chemical elements exhibit vastly different physical properties based on how their atoms are arranged. In diamond, pure carbon uses an sp3 hybridized tetrahedral network. Because every atom is tightly interlocked in 3 dimensions, the material is extremely hard and acts as an electrical insulator. Graphite uses sp2 hybridization to form flat 2-dimensional layers. Because it contains free-floating electrons between these layers, it conducts electricity and is soft enough to flake off onto paper. Buckminster fullerene represents a 3rd structural configuration, where 60 individual carbon atoms form a hollow sphere resembling a soccer ball. Physical strength and electrical conductivity derive strictly from this structural layout. Design dictates the material's properties as much as the raw element itself. When carbon bonds exclusively with hydrogen, it forms hydrocarbons. These systems are categorized as either saturated or unsaturated. Saturated alkanes contain only single bonds, meaning their connection slots are full. Unsaturated alkenes and alkynes contain double or triple bonds, giving them the capacity to accept more atoms. Because carbon chains in different ways, we encounter isomerism, compounds with the same formula but different structural blueprints. C4H10 can be laid out in a continuous sequence of 4 carbon atoms to form N-butane. Drawing this chain with a visual bend does not create a new isomer. Bending the chain downward still leaves all 4 carbons in the same sequence, resulting in the exact same molecule. A true isomer requires a change in the connection sequence. By attaching 1 carbon to the center of a 3-carbon base, we create isobutane, a branched structure with entirely different properties. Mapping the precise sequence of connections is the only way to accurately identify a molecule's true identity. Carbon compounds follow predictable reactive categories dictated by these structural rules. In combustion, saturated hydrocarbons react rapidly with oxygen, breaking apart to violently release water, carbon dioxide, and energy. An addition reaction requires an unsaturated hydrocarbon. It breaks open its double bond to capture new atoms, transforming into a saturated structure. Because saturated alkanes have full bonds, they must use a substitution reaction, ejecting an existing hydrogen atom to make room for chlorine. A molecule's internal saturation level dictates how it interacts with external elements. Carbon's inability to form ionic bonds forced it to share 4 electrons and link with itself, creating the foundational rules of organic chemistry. That sharing process defines the molecule's geometry, allowing the same element to manifest as vastly different physical materials, like diamond and graphite. This hierarchy determines everything. The density of the bonds controls saturation, which in turn dictates whether the molecule uses addition or substitution reactions. Mastering carbon chemistry depends on understanding a handful of predictable structural rules that govern every complex molecule.